you, Isam. Thank you for the very generous introduction, and I'd like to thank the DSAA organizers for inviting me to give this talk, and I hope that there will be plenty of questions. We have a lot of time, so please feel free to use the chat or the Q&A to ask questions, and I'll try to check that a few times during the talk. I'm going to share my screen now, and so you'll see my slides. So the title that I'm using is Unbiased and Optimal Learning to Rank. And I think most people have a general idea what unbiased means and what optimal means, and I'm going to make that precise during the talk. And then learning to rank is a well-known research area in machine learning. Essentially, given a set of results for a search query, how should those results be ordered? In what sequence should they be displayed? The particular learning to rank problem that I'm going to be talking about is a little bit different from the standard learning to rank problem. So I hope everything will be clear. So this is research that I did personally when I was at Amazon. This is a little bit more abstract and general than most of the things that my team worked on at Amazon. And as Isam said, as well as Goldman Sachs, I'm an adjunct professor at the University of California, San Diego. And if anybody wants to get in touch with me by email, my UCSD email is very simple, easy to find. It's just elkan@ucsd.edu. Okay, so I'd like to point out that the major internet companies, for their central problems that they're trying to solve, that there's a lot of similarity in these central problems. So they think of a search engine like Google or Bing, for example. So the results from Google are personalized, at least to some extent. So the input to the core Google algorithm is a query, which is some words, a topic that the user is interested in, but it's also the identity of the user, maybe the history of previous queries by the user. So the search algorithm is given a user, the identity, given a query, and then has to select results from a large database, and then has to display those results, and has to display them in a particular sequence. Usually the result that's most likely to be interesting to the user should be displayed on top. Now, if you think about a company where the central problem is recommendations like Netflix, so concretely there you have a user, and the user has watched various videos recently, and then now the company wants to recommend additional videos or movies. So you can think of the recently viewed videos as being a query, and then there's a database of other movies and videos, and then some of those should be selected, and then they should be displayed in a certain order. Presumably the video that the user is most likely to want to watch next should be the one that's most prominent. Think about advertising on the internet. So if you're a Yahoo user and you're looking at a web page, and there are various positions on this web page where advertisements can be displayed, and the web page itself is like a query. If the web page is a story about cars, then the advertisements will likely be about cars also. So the web page is a lot like a query. There's also the identity of the user, maybe what web pages the user has looked at before, and so on. So again, Yahoo needs to select advertisements from a large database and then display some of them and choose which positions to display them in. And then finally, if you think of a social media company like Facebook, so you're browsing Facebook on your phone or in a web browser, and Facebook knows your identity, and then it's choosing some updates or stories to display. And there's many different updates that could be chosen. So which ones should be chosen and in what sequence should they be displayed? So all these four problems have a lot of similarity. And so this talk is about a general solution to these four ranking tasks. So the way I'd express the general task in English, we're given a query. The query may include a context, so that could be a history, for example, of previous actions. And the context may include the identity of a user, and then there's a database of potential results, and the algorithm needs to choose which results from this database, and those are the ones that will be displayed. And then there are various positions in which results can be displayed, and the algorithm needs to decide which results to put in which positions. So here's an advertising example from Amazon. Let's say that you're looking at an Amazon product information page for a computer keyboard. Then in the middle of that page, there's going to be sponsored products related to this item. So sponsored means advertising. And this item, which is the main product on the web page, is the query. And then these particular 3 other keyboards are the ones that an Amazon algorithm chose as the most relevant to be displayed. And they were displayed in these 3 positions from left to right. So here's a more precise statement of the task. So we're given a query Q, and we need to decide which results X to show in which positions J. So I'm always going to be using Q to refer to a query, and Q will include the context, include the identity of the user, everything else that may influence which results are chosen. And results will always be called X, and then the positions in which they can be displayed will always be called J. And what we're really looking for is a ranking function. And this ranking function R, one input will be the query Q, another input will be a potential result X, and then the output of the ranking function is the position in which X should be displayed, conditional on the query Q. And of course, typically the database will contain millions of potential results, and only a few of them will be displayed. So there'll be a special position, which is the do not display position. But conceptually, for every query Q, for every result X, there's a certain position in which that result should be displayed. And what we want to obtain is the best possible ranking function. The ranking function, sometimes I'll call it an algorithm, like could be called the search algorithm, and sometimes I'll call it a policy, because it maps every potential state, which is an X, Q pair, it maps that state into an action, which is the position at which to display X. Let me see if there are any questions so far. I'm just looking for where I can see the questions. I may have to stop screen sharing in order to check for questions.
I'll let you know, Charles, no worries. Please keep going. I'll let you know.
Yeah. Can people see my full screen again?
Yes.
It's sharing full screen, good. Right. So that's a more precise statement of the task. So let's think about some important considerations that a method for solving this task should deal with. So I'm calling these 4 important phenomena, and they're rather obvious, but it's good to make them explicit. So the first is that some results are more relevant than others. This is the basic idea that search engines want to identify relevant results. They want to identify X that are relevant to the query Q. And I think a more general word than relevant is attractive. So if we're an advertiser and we're showing advertisements, we want those advertisements to be attractive to the user. And maybe from the user's point of view, the user wants the ads to be relevant, but from the system's point of view, maybe attractive is a more precise word. And then another very fundamental phenomenon is that some positions are more prominent than others. The most relevant search result, intuitively, we should put it in the most prominent position, which intuitively is the top position. Now, relevance and prominence both depend on the query. It's obvious that relevance depends on a query. It's a little bit less obvious that prominence depends on a query. But this is actually a well-known phenomenon. Some queries, people just want to get the answer very quickly. Like they'll be searching for the address of the nearest Starbucks. And then if the answer is not in the most prominent position, people may not even look at the next positions. But then other queries are more research oriented, and the users will tend to look carefully at all the top results. So the variation in prominence between different positions can depend on the query. Then the fourth phenomenon is that queries can include a lot of information. In particular, they can include what I've called context, and that could be time of day, that could be geographical location, it could be the identity of the user, the history of the user, it could be the surrounding content. You know, if we're putting advertisements on a web page, then the surrounding content is really important. It could be the device type. Maybe the most attractive results are different for Android users and for iPhone users. And so there's a lot of context in general. So what are the issues with previous research? What are the problems that remain unsolved? Well, one issue with previous research is that almost all of it is just different methods for choosing recommendations, or different methods for ranking advertisements, or picking search results, or fitting a news feed. So these different problems haven't been considered in a unified way. Then for search algorithms in particular, one limitation of previous research is that the positions are assumed to occur in a linear layout, from the best position to the worst position. And typically the best position would be the top position, or it would be the furthest left position for a language that is read from left to right, like English. But if you think about putting advertisements on a web page, the positions where you can display advertisements don't occur in a linear layout. And it is not obvious which position is the most visible and which position is the least visible when the positions in the display are not linear. Another limitation of previous research, at least the research that I've seen, is that when it addresses the issue of position bias, which I'm calling prominence, then that is assumed to be the same for all queries and contexts. And as I just explained when I was talking about the previous slide, it's intuitive, and there's experimental data that confirms that position bias is not the same for all queries and contexts. Now, the title of this talk is Unbiased and Optimal Learning to Rank. So if you look at the research that is under the name Learning to Rank, it ignores position bias. It's really learning to re-rank for relevance. So it's taking a small set of potential answers to a query, and then the research question is how should those be re-ranked, but it doesn't, it's how should they be re-ranked according to relevance and not paying attention to position bias. And so if you want to learn to rank but taking into account position bias, then that's what I'm calling unbiased learning to rank, because we need to remove the effect of position bias when we're trying to estimate attractiveness or relevance. Now, in order to make progress, we need to identify a precise goal. And a goal is a metric. So what is the metric that we're trying to maximize? And think about an e-commerce company, or think about an advertiser. So one potential metric to maximize is clicks, but people might click on a lot of products and look at those products, but not actually buy those products. So maximizing clicks is different from maximizing purchases. And maximizing purchases is different from maximizing revenue. If you want to maximize purchases, then you're going to be displaying low-priced products and people will buy a lot of them. If you want to maximize revenue, you may be displaying higher-priced products, because then each product that gets sold contributes more revenue. And then maximizing revenue is not the same thing as maximizing profit, because different products that are sold may be very different in profit, even if they're the same in revenue. And when I look at previous research, I don't see the maximization objective being explicit. And so I want to have an explicit metric, and then to let that metric be changed to represent alternative goals. So here's the formalization of the situation, the scenario that's going to let us make progress. So remember, X always refers to a result. And the conceptual model is that for every result X that is displayed, the user may or may not respond. And a response might be a click, or it might be a purchase, or it may be something else. But I'm going to assume that responses are binary. So the response will also be called the action, and it's always A equals 1 or A equals 0, just either response or no response. So then I can write down a probability for the response. So that's the probability that the action equals 1, and that's going to depend on X, it's going to depend on the position J, and it's going to depend on the query Q. So the query Q is the indication of what the user is interested in, and the action of the user is going to depend on what they're interested in, as well as on whether our algorithm is displayed an attractive X and displayed it in a prominent position J. Now, that is the website or the algorithm or the company, so we receive a benefit if the action is 1. Essentially, we want the users to take actions. We want the users to click, or we want them to purchase. Or if we're a news site, we want the users to read the article. And the benefit for different results and different queries may vary. So I'm calling the benefit V. V stands for value. And V is 0 if the action is 0. So V is, there's no benefit if there's no action. If there is an action, so A equals 1, then the benefit is some function of X and Q. Now, let's think about the total benefit. So for a given query Q, then the total benefit is the sum over all possible results of the benefit of that result with this query Q, and then the expected total benefit. Each of these values, we get it with a certain probability. The probability we get the value is the probability that the user takes the action. And so the expected total benefit is the sum over all results X of the benefit of X times the probability of action equal 1 given X. And X is displayed in position J, and then the query is Q. So I hope this is clear, because this is going to be the foundation of what comes next. So let's think about a single fixed query Q. And so what I've written at the top here is the same expression as before, which is the expected total benefit for query Q. But now, this benefit is going to be different for different ranking functions. So a ranking function is capital R, and what it does is it chooses the position J for each X. And if the ranking function puts the good X's in the good positions, then we're going to have a large expected total benefit. And if the ranking function puts the wrong X's in the prominent positions, then these probabilities are going to be small, and we're going to have small expected total benefit. So our job is to choose the best possible ranking function R, which maximizes this expression. So what's the average goodness of a ranking function? Well, it's an average over all queries. And queries follow a certain distribution. The queries come from users. And so our algorithm doesn't control the distribution of queries. It just has to live with that. So let me call the distribution of queries capital D, and then the average goodness is an expectation where query Q follows this distribution D. And then on the middle expression, what's inside the expectation is just what I wrote at the top. And then, of course, this expectation is just a definition. So how do we use data to estimate the average goodness? Well, the simplest possible estimator is the empirical estimator, sometimes called the plug-in estimator, where we have a data set of queries Q, and those queries are drawn from the distribution D, and then for each query that actually is in our data set, we can look over all results X, and we see which position J was X displayed in. And then we see, well, actually, did the user actually respond or did they not respond? That's just yes or no, 0 or 1. And so that's the indicator function. And so replacing the probabilities with the indicator function of an actual response gives us the empirical estimator of average goodness. And being able to estimate something is the first step towards being able to optimize it. Right. So, you know, the user situation is that we have data which we collected following a historical policy R. So whether it's a search engine or whether it's an advertising algorithm, there's already some algorithm that's being implemented. And that algorithm that's being implemented now is what we can call the historical policy R. And what we want to do is use the data that we collected following R to invent a better policy, which I'll call N for new. And the new policy is off policy because compared to R, it's a different policy. So we want to invent a better policy N, but we don't have any data that was collected according to N. So this is what's called being in the off policy scenario in reinforcement learning. And off-policy learning in general is more difficult than on-policy learning. So what do companies do in practice? Do they do off-policy learning? No, in practice they don't. What they do is what's called A/B testing, which is the same essential idea as a randomized clinical trial in medicine. So there's 3 steps in A/B testing. So first, you have an idea for a new policy N. So there's an existing policy R, but somebody has a conjecture that a new policy N might be better than R. Then the next step is to implement the new policy, which is expensive. And then the next step is to do A/B testing of the 2 different policies. And what that means is to take the traffic that you're getting from real users and send half of that traffic to the old policy, send half of it to the new policy. And then when you have enough examples of users with both policies, then you use the empirical plug-in estimator to measure the benefit of each of the policies, and you find out which policy is better. So this is exactly what happens in clinical trials in medicine. So there's a certain current standard treatment for a disease, which is the policy R, and there's a potential new treatment, which is the policy N, and then the new treatment is implemented, and then you get patients, and half the patients get the old treatment, half of them get the new treatment, and when you've seen enough patients, then you can measure whether the patients with the new treatment are doing better on average. So A/B testing, it's slow, it's expensive, and even if the new policy is better than the old policy, the new policy is still not optimal. So in practice, A/B testing never ends. If the new policy is better, it gets adopted, it becomes the old policy, and then people start to think of even newer policies. Okay. So we can actually find an optimal policy if we make certain assumptions. Of course, it's impossible to find a policy that is optimal in an absolute way. But if we're willing to make some assumptions, then that simplifies the problem. So the basic quantity that we need to estimate is the probability of action by the user. And before I wrote that as the probability that A equals 1 conditional on X, J, and Q. But if you think of, say, the action being clicking on a result X, then that may be affected by other results and other positions. Maybe the user is only ever going to click on a single result. Then if the user clicks on one result, then by definition, the probability of clicking on any other result is 0. So in general, the probability of the user taking an action can depend on all the results and all the positions. But the first assumption that I'm going to make is that, in fact, the probability doesn't depend on other results and other positions. So the probability is independent for each X and J. Now, so that's quite a strong assumption, but it's not too strong. It can be approximately true in practice. Now, the next step is to, think of, how the user is behaving. So conceptually, if the user is going to take an action for the result in a position J, the user has to at least look at the position J. If they don't look at what's in J, then they can't take the action. So let's just define a binary event called view, which means that the user examines the position J. And we can't necessarily observe whether the user is examining a position, but we can still define this event conceptually. And actually, people have done eye tracking studies to actually measure what the users look at on a web page and what do they not look at on a web page. So if you had eye tracking data, then you would have actual data for the binary event view. But even if you don't have that data, it still is meaningful to think of it conceptually. So the assumption that an action can only happen if a view happened before. So I write that as the probability that the action is 1 given X, J, and Q. It's the probability of view, which just depends on J and Q, and then times the probability of action, which also depends on X. And now the probability of action is conditional on the view. And so probability of action equals 1, conditional on view equals 0. That probability equals 0 by assumption. Now, next assumption I'm going to make is that attractiveness is independent of position. So the second factor on the right-hand side of the middle equation, so I'm going to assume that the probability of action equal 1, conditional on view equals 1, and conditional on X, J, and Q. In fact, it's independent of J. It's the same for all J. So that second factor, I'm going to write it just as probability of action equal 1, conditional on view equals 1, and conditional on X and Q. So the idea is that if the user is looking at a position, then the position is no longer important for whether they find the result attractive. And that's also a somewhat reasonable assumption. So in words, I can say the central assumption that intrinsic attractiveness is independent of position and also of the attractiveness and prominence of other results. And in writing that down as an equation, so the probability that the action equals 1 given X, J, and Q. So it's the product of the prominence of J, which I'm just going to write as the function B of J and Q. The prominence times the attractiveness, the intrinsic attractiveness. So the intrinsic attractiveness, I'm writing it as a function R of X and Q. So it's B for bias and R for relevance. So the assumption is that the bias doesn't depend on X and that the relevance doesn't depend on J. So this probability of action can be decomposed into these two different factors. All right, so now let's think about how we can go from an old policy R to a new policy N. So let's write down the goodness of the new policy N. So it's an expectation over the same distribution D, because the policy doesn't influence the distribution of queries. That's just given by the users. And then for each query Q, the goodness is the sum of all possible results of the probability of action given this result, given the position the result is in, given the query Q, times the benefit. And the new policy N puts X in position J. So how can we estimate the goodness of a new policy without actually collecting data using the new policy? Well, there's a mathematical trick that we can use, which is well known. It's sometimes called, importance sampling or importance weighting. So I take that definition at the top of the goodness of the new policy, and then I put an extra factor in the formula, and this extra factor is a numerator divided by a denominator. The numerator and the denominator are the same. So this extra factor always has the value 1 with the assumption that the denominator is non-zero. It's undefined if the denominator is 0. So with this numerator and denominator, they cancel each other. So the formula at the bottom is the goodness of the new policy. And then I can manipulate this formula at the bottom. So I'm going to abbreviate. So J will be the old position of a result X, and K will be the new position of the result X. And the goodness of the new ranking function, so if you look at the top right of the left-hand side of the equation, so that's B of KQ times R of XQ. So that's the probability of action for X being displayed in the new position. And then the two factors in red are actually the same. So what's the denominator that's in red is the denominator that came from introducing the fraction that was on the previous slide. This is just, so BJQ times RXQ is the same thing as probability of A equals 1 given XJQ. So now I can cancel the R of XQ on the top and the bottom. So I'm left with an expectation over queries Q, sum of all results X for a given query Q, and then what's inside here, the probability is the probability of the action according to the old policy. And so I can now take an empirical plug-in estimator of the right-hand side of the equation at the bottom. And that empirical plug-in estimator, because it uses probabilities according to the old policy, I can evaluate it using data that was collected according to the old policy. So I can use data that's collected according to the old policy to evaluate the goodness of a new policy if I know these position biases. So if I know the bias of position K and I know the bias of position J, and then that provides a multiplier, which is an adjustment factor. So the empirical estimate of the goodness of N, it's the sum over queries, then sum over results for the query, indicator of whether the user took the action when X was displayed in the old position, and then multiplied by this weighting factor. So intuitively, if the new position is more prominent, so B of KQ is bigger than B of JQ, then there's an additional contribution to the goodness of N. And if the new position is less prominent, B of KQ is less than B of JQ, then there's a reduced contribution to the goodness of N. So the algorithm is to collect data points using the old policy, then reweight each data point with the multiplier, and add up the weighted benefits that are observed in the cases when the user takes the action. And this is the algorithm for estimating empirically the benefit of a new policy. So this can take the place of A/B testing, at least in principle, and when the assumptions that I outlined are valid. So what do we need to estimate from data? What do we not need to estimate from data? So usually the benefits are known, so we don't need to estimate them. So if we wanted to maximize clicks, then the value of every click is just 1. And if we wanted to maximize revenue, then the action would mean purchase, and then the benefit would equal the price of whatever was being purchased. And the sum of all these prices equals the revenue. If we want to, we can make different clicks have different values. A click where the user bounces back very quickly has a lot less value than a click where the user spends a long time reading whatever they clicked to. And for e-commerce, I won't go into it now, but in general, revenue is a better objective than units sold and a better objective than profit. So if the action A equals 1 means purchase, and we said that the benefit of every purchase was the same, then what we would be maximizing would be the number of units sold. And that's not really a good thing to maximize. It's much better to maximize revenue. So what do we need to estimate from data? Well, we need to estimate the position bias, the B function. And we don't directly need to estimate the relevance, but it's going to be useful to do that. So this is a model that we need to fit to data. So we have data of, a result X, a position J, a query Q, and then whether or not there was an action A. So this is like the data that we might use for logistic regression. It's the most standard possible type of machine learning, supervised machine learning problem. Is just learning a binary probability function. But there is an important difference because we're making an assumption about the structure of this function. We're making an assumption that the left-hand side is the product of 2 functions. And those functions themselves have meaning. So the prominence B, that's the probability of view. And then the relevance R, that's the probability of action given view. And as I said a few slides back, usually view is a latent variable. We don't observe it. We can conceptualize that it exists, but we can't actually observe it in data. We observe the actions. And view is a latent variable, and standard software can't fit models with latent variables. So in fact, we can't use any scikit-learn function or any other standard supervised machine learning model for this problem. One thing to note is that the best possible model is not actually unique because we have this multiplication on the right-hand side. If you take the first factor and inflate it by a constant and you divide the second factor by the same constant, then you get a perfectly equivalent model. And so the solution to this optimization problem, to this learning problem, is not going to be unique. But that's not a problem in practice. So here's the model that we want to fit to data. We have data for actions A, Q, J, X, but we want to fit a model which is this product with this latent variable view. So one thing that we could do is just ignore the latent variable and fit a logistic regression function of Q, J, and X. And actually that is useful in practice, but theoretically it's incorrect. The most common way of fitting a model with a latent variable in machine learning is to use expectation maximization. But we want to fit this model to data with millions or even billions of examples, because we're going to if we have a real search engine or recommender system, then there's going to be billions of recommendations which we want to fit our model to. So expectation maximization is just too slow. And there are probabilistic programming languages that are available now. One of them is called STAN, where you can write down a model like this, and then there's a compiler which will actually compile the model into an algorithm for fitting it to data. But the difficulty with these probabilistic programming languages is that they don't scale to tens of millions of data points. So we need a solution that's different from these three possible solutions. So it turns out that we can use deep learning software for this. Even if we are not using neural network models, we can define the model in the deep learning software, Keras or TensorFlow or PyTorch, and then use the deep learning software to fit the model. So the idea of how you do it is that, okay, we're defining a network, and you can call it a neural network if you want to, but it's not really neural. And the output of the top layer is going to be the probability of action given Q, J, and X. And the loss function that we'll use is log loss or some other loss function that's appropriate for learning a binary probabilistic model. And then we define the input to the top layer to be the product of the outputs of two subnetworks. And then the subnetworks can be anything that we want. If we make the subnetworks be linear, then each of them individually is a logistic regression, and then the output is the product of those two logistic regressions. And then it turns out that in order to train this model, generally in order to train a neural network, what you need to do is backpropagate derivatives from the output of the top layer down to the internal layers. And so here the output of the top layer is a fixed function. It's the function multiply. And it turns out it's easy to backpropagate derivatives through a fixed function. And Keras and PyTorch and TensorFlow will do this for you. And they do scale to very large training sets. So that's how I implemented this in practice. But I haven't yet answered the question of how to find an optimal ranking function. So the first thing to notice is that conceptually, we can find the optimal policy separately for each query Q. And then if we're looking at a single query Q, then the definition of the optimal policy is the argmax over n prime of the goodness of n prime, where n prime is a ranking function that puts a position j for every x in Q. So what's inside the summation is a probability times a benefit. And the benefits are fixed. The probability is the prominence times the attractiveness. So we want to maximize essentially the prominence times attractiveness. So if you think about it for a minute, the optimal policy is greedy. You put the most attractive result in the most prominent position. You put the next most attractive result in the next most prominent position, and so on. So the algorithm that actually for the optimal policy is quite simple. It's to figure out what's the attractiveness of all possible results and then show the results in descending order of attractiveness. And this is quite an intuitive algorithm. I think most people would have done this, would have converged on this without having a precise mathematical reasoning why it's optimal. Actually, we need to sort the results by the attractiveness times the benefit, because what we want to maximize is the benefit to the system. And so a high benefit, low attractive result might be better to make it more prominent than a high attractiveness, low benefit result. So concretely, first, we're given a query Q, and then we're given certain available positions J. So the first thing to do is to estimate the prominence for each available position. Then we find a subset of reasonable candidates X, estimate the attractiveness for every X in the subset, sort the subset by attractiveness times benefit, and then whatever the position with the highest prominence, that's where we put the result with the highest estimated benefit times relevance. And then the second best position gets the second best result, and so on. So this is actually the optimal ranking function, given the assumptions that I talked about before, and given that you actually can estimate prominence and attractiveness. So how can we investigate this process, this method, using real-world data? Well, all the companies that I mentioned have data sets of billions of examples that would be usable for fitting the model that I talked about. But since there were some fiascos many years ago, no major company will ever release search engine data or recommendations data or the sort of social media viewing data. So there's only one data set that I know of that contains the information that is needed to evaluate this method, where the data set is public. That's a data set that was published, I think, in 2016 by Diginetica, which is a Russian consulting firm. And this is anonymized e-commerce data. If anybody knows any other data set which has these quadruples of, an action A equals 1 or A equals 0, then a product X and a query Q and a position J, I would love to hear about any other data sets that have this pattern of these 4 tuples. So in this particular data set, a query is a product category, and then a result is a product for sale, and the result pages normally have 20 positions. So that's J equals 1 to J equals 20. And the data are the 4 tuples I just mentioned. So an X, a J, a Q, and then the action A, which is 1 for click or 0 for no click. And let's say that our goal is to maximize clicks in the top 10 positions by selecting the most attractive 10 products to display. So different queries Q will have different most attractive products, different positions will have different prominence, and we essentially want to put the most attractive products in the most prominent positions. So we have training data and we have evaluation data. So the training data, I'm using data that was collected in the first 4 months of 2016. So this is 409,000 queries. And there were 1,100 different product categories. So there were 1,100 different queries, and there were 409,000 total queries. So like on any search engine, the popular queries get repeated many, many times. There was some historical variability in which results were displayed for the same query. You can do the same query on 2 different days, and there may be different results. So if the same results were always displayed for the same query, then there would have been just 22,000 different QX pairs. But in fact, in this data, there were almost 34,000 different QX pairs. And there's a total of about 8 million training examples. That's 409,000 queries times approximately 20 training examples per query. So 400,000 times 20 is 8 million approximately. And the individual training examples are these 4 tuples. The data set is very unbalanced, of course. Of the 8 million training examples, about 150,000 had clicks, and the rest didn't have clicks. So the raw click rate was about 2%. If you compare this data set to those that are used in research on learning to rank, then as I said before, they don't have position data, and the data sets are typically tiny, less than 1,000 queries. And so not really useful for investigating algorithms that would be useful in real applications. Now, 8 million training examples is actually still small data here. So I'm simplifying the model to make prominence depend on the position J, but not depend on the position Q. So the function B is now a function of J only. In theory, it could be a function of J and Q. And we know the identity of products, but we don't know any of their features. So we have to just treat each product as being a separate, unique identity. So there's 20 parameter values to learn. That's the different prominence of each position J. And then there's 33,861 parameter values to learn, which is the attractiveness of each X for each Q, where QX actually was observed in the data. So this is fitting a model that has about 34,000 parameters to a data set of about 8 million training examples. And using TensorFlow on a laptop, that only takes minutes. Then for evaluation, in most real-world problems, it's important that the evaluation data should come later in time than the training data, because the real world is always changing. That's called non-stationarity. So here, validation is 186,000 queries in the month of May. And there were for each of these queries, there were 10 results that were actually displayed by the e-commerce site historically. And those 10 results gathered 34,000 clicks. Now, if we displayed, so there were 34,000 clicks according to the historical policy R. Now, if I used the optimal policy N, then that optimal policy would have yielded 45,000 clicks. So that's a 30% improvement, which is definitely of commercial value. And I think it's quite impressive because this is data from a real world e-commerce website from a consulting firm. So the historical results were already optimized. We don't know what the historical policy R was, but it was a real world policy which had presumably been at least somewhat optimized using A/B testing. But the policy N would yield 31% more clicks. So if the goal is to maximize clicks, then it's possible to have more clicks. It's interesting to look at the trained model and to try to interpret it. So on this chart, so the 20 positions on the horizontal axis, so from position J equals 1 to J equals 20. And the red line shows raw click probabilities. So there are more clicks in the top position, next most clicks in the second position, and so on, which is not surprising because the historical policy is already trying to put the more attractive products in the higher positions. Now, the blue line shows the estimated position bias, the estimated prominence. And so this is closely related to the raw probabilities, but the slope of the blue line is a little bit more shallow than the slope of the red line, at least for the higher positions. So what this says is that the raw click probabilities decay faster than the prominences. And the reason for that is because the raw click probability is the product of attractiveness and prominence, and the more attractive products are already in the higher positions. Now, one of the strengths of this method is that it does let position bias depend on the query. And I already mentioned the hypothesis that for some search queries, people will look at all the top results, and other search queries, people will only look at the first result. And there's a similar hypothesis in e-commerce that if you have an expensive purchase, then users will investigate their choices more carefully, and so there'll be less position bias. But if you have a cheap purchase, then people just want to buy it quickly, so there'll be more position bias in favor of the top position. So this is a hypothesis that we can investigate with the data. So we can fit a more sophisticated model where the bias B depends on the position J and also depends on the price of the query. So every query has got a certain average price. And so we can separately for each query product category Q calculate the average price of products in that category and then fit a model where the prominence depends on this average price. So this is the result of that, where what I'm actually doing is fitting 3 different models for prominence. One model for the low price queries, one for the mid price queries, and one for the high price queries. So blue is prominence for low price queries and green is prominence for high price queries. And the prominence, the view probabilities, they decay much faster for cheap products than for expensive products. So this supports the hypothesis that position bias is a bigger phenomenon for cheap products, that for expensive products, people are more likely to look at multiple positions. All right, so that's the end of explaining the method and some experimental results. Let me finish by talking about limitations and strengths of the method. So here are 4 limitations. So the first is that in order to use the method, you have to log all displayed results. You have to log their positions, even if those results are not clicked. And it's quite common, many systems will log clicks or log purchases, but they won't log non-clicks. And in order to do this training, you need to log the non-clicks. Another limitation is a general limitation of off-policy learning methods, which is that if a result is never displayed historically, then the method can't learn that it would be a good result. And then the third limitation is really from a research point of view more than from an application point of view. So from a research point of view, we'd like to compare against previous methods, but there isn't a particular previous method that I can compare against. If anybody has one to suggest, I'd like to hear about it. And even more, if anyone has a better data set, a bigger data set than the Digenetica one, I'd like to hear about it. And then the final limitation is the central assumption of the method. So if the relevance of one result influences the view probability of another position, then the central assumption is false. If the central assumption is false, it doesn't mean that the method is useless. What it means is that the policy that you get from it may no longer be optimal. It'll still be a good policy, but it won't be optimal, because an optimal policy would need to take into account how the relevance of one result influences the view probability of another position. But what are some advantages of the method compared to previous research? Well, one is the unification. It's the same method for recommendations, advertising, search results, and filling a news field. And the data that's needed is easy to log. And then another advantage is that the positions don't need to be in a linear layout. And this is important with web pages nowadays, where there can be information at many different places in the web page. There's 2 mathematical advantages. The first is that the optimal ranking function is deduced from a maximization objective, and the objective can represent many alternative goals. So with different goals, we're going to get different optimal ranking functions. And then the multipliers that we need for importance weighting, it's the ratios of prominences. And these ratios are not extremely large or small, and so they don't cause very high variance in the estimators. There are other applications of importance weighting, which in practice are very difficult to make work, because the multipliers become so big or so small that you get very high variance in the estimates, but that's not a problem here. And finally, there's a lot of flexibility in modeling queries and context. So a query is not just a query, it's also the identity of the user and anything else about context. which can include time of day, type of device, and more. And we can use any model for prominence. That's probably a view. And the model of prominence can use any characteristics of queries Q. And then the model for attractiveness, which is probably of action, that can also use any properties of the query Q. So it can use all observable attributes. And by using attributes of queries and positions and results, then the method can generalize to really solve the cold star problem. So it can generalize to new queries, new positions, and new results. I've said this already. All quantities can vary depending on the context and or the query. That's the position biases, the benefits, the attractiveness. And for an e-commerce firm, for example, the benefit of a customer purchase is higher in a new category than in an old category, because an e-commerce company would like to get customers to buy products of more and more different types. So that's how benefit can depend on the query Q and the history of the customer. And then relevance may depend on geolocation as well as on query text. Okay, I'm going to stop here and take questions.
Great. Thank you so much, Shaz, for a very informative presentations. Personally learned a lot about it. This is an exciting topic and a new technique that you presented. Let me take the mantle of being the moderator and ask the first question. You probably already addressed it. When you are trying to identify bias, that's typically not an easy problem in the context of other domains aside from e-commerce, where you're assuming the new product is known and it has a prominence. How would you formulate that if you are looking at the medical problem, for instance?
So this is a very narrow notion of bias. This is position bias. And really the only reason I'm using the word bias is because it's been used in previous research. It's called position bias. And I think a more neutral word is prominence. Different positions have different prominence. And I'm not sure that the notion of position really is applicable in medical research. I need to think about that, but I think this is certainly very different from the bias that people might think of in social situations, like bias based on socioeconomic status.
I see, that makes sense. Now, A/B testing is a gold standard in many domains, and the presumption that is being used, again, take us back to that same question about bias, that you are assuming there no bias involved, but in the ranking algorithm you presented, prominence,
yeah,
I mean, by virtue of bias, is part of the design of that problem. How do you reconcile the two approaches? Now, we are still waiting for a vaccine because we want an unbiased test, assuming an equipoise between what a population is not going to get and a population is going to get that vaccine, for instance.
Yeah, so I think here, actually, the A/B testing is happening at a higher level. So the A/B testing is between two different policies, say R and N. And
okay,
each of those policies is going to deal with prominence in a different way. And then the A/B testing will reveal which one deals with prominence in a better way. But the two different policies, each of them is going to have its own way of dealing with prominence, and each of them is also going to have its own way of dealing with relevance. And the one that's better is the one which has the better combination. So the bias that's in prominence is sort of in an inner loop compared to the bias that you eliminate in A/B testing by doing randomization. And some users will be exposed to the algorithm R, and some will be exposed to the algorithm N.
That sounds great. Let me see if any of the attendees have questions. Can you please raise your hand? We'll give you the mic to talk if you don't like to write. Okay, while waiting about them to think about this, the sample size requirements is always a concern with applying machine learning to different domains. E-commerce, obviously, there is this data set that you mentioned that is a very large data set. But if I would like to apply the same algorithms to a domain where no such data sets with that sample size, I understand there is a skewness in these data sets, and that's where probably the requirement for the large sample set. How can be applied? Is there a practical way of doing it when you have a limited sample size?
Well, if you have a limited sample size, but you also have a very limited range of queries Q, results X, and positions J, then I think the method will still be applicable. And I was talking about the two subnetworks, and the more you simplify the subnetworks, the smaller the sample size you need also. And for the first experiment that I showed, I simplified the subnetwork for prominence so that it didn't depend on Q. So I think that the method is still applicable with a small sample size, but you'd need to simplify the models so that they don't, so you can avoid overfitting to the small sample size.
If we want to get a little bit onto nuts and bolts, how did you design the subnetworks in terms, I understand it's not a neural network, but it's using a network architecture. How did you estimate number of layers, number of nodes, connections in these cases?
Actually, in these experiments, the subnetworks were not neural networks. They were logistic regression models.
Oh, regression models, okay.
Yeah.
How did you design the number of parameters associated with them? How many you need?
There was really no choice about that because this data set doesn't include a lot of features. It really just includes unique identity. So there are 1,100 different product categories, and I don't know what those product categories are. I just know that there are 1,100 different unique categories. So then there was, then that gives me 1,100 parameters and so on.
Okay, I see. Thank you for clarifying that. I don't see questions yet, but we still have 1 more minute to ask you one additional question. How a company like Goldman Sachs apply a ranking algorithm for their hedge funding recommendations? If you can answer something like that.
The answer is that for something which is a high stakes recommendation, like recommending a hedge fund, it's done, by human analysis and by humans combining many different criteria and coming up with a qualitative conclusion. Algorithms like this are useful in the big data situation where the penalty for being wrong on any particular individual prediction is small. So for a company like Netflix, they use algorithms for recommending videos to viewers, but I don't think that they use algorithms for deciding which TV series to invest $50 million in creating.
Okay, so it remains an open question now. Okay, I accept that. Thank you so much, Charles. Much appreciated on behalf of everyone. We really enjoyed your talk and we look forward for future association with you. Please contact Dr. Elkan on his email address. Still responds to the email at USSD if you have any inquiry that you didn't have a chance to present them. Thank you very much and have a great day. Thank you.
Thank you.